and she will be speaking about how to bounce your canon permutation. So
Exactly.
let's welcome Danai.
Thank you, Margaret, for the introduction. And everyone, thanks everyone for being here for this talk. It's going to be a brief talk about my recent preprint with Krishna Menon, who is a postdoc at KTH. And it's going to be about canon permutations and their descent polynomials. So I suppose most of you are familiar with the basic terms, but and hopefully the examples are illustrative for those that are not. But feel free to also interrupt if there's any short clarification you need. Okay. So what are those canon permutations? You can think of them as a pair of a dict path and a regular permutation. And if my dict path, let's say that is drawn here diagonally, these are the up steps that are diagonally up and then down steps, and it has semi-length 6. So that means 6 up steps and 6 down steps. So if my dict path has semi-length 6, I also start with a permutation of length 6. And how can I use this permutation to label the dict path? Well, one idea is to take each of the entries of the permutation and put it on the up steps of the dict path. But then what about the down steps? Well, I can do the same, right? And that gives me a labeled dict path with labels that its number repeats twice in the labels. One more example. So in general, a canon permutation defined by example here is a permutation where I start with a dict path and a regular permutation. So if my dict path has semi-length n, I start with a permutation of length n. And then I use this permutation to label the up steps in the same order from left to right and the down steps. And then I read the word that gets out. In this case, it's 3, 3, 5, 2, 1, 5, 2, 4, 1, 4. Right, so this is my canon permutation for this dict path and pi. So these are always permutations, essentially multiset permutations for the multiset consisting of numbers from 1 to n, in this case 1 to 5. It's repeating with multiplicity 2. Okay, great. So these are the permutations I want to play with, these multiset permutations that come from dict paths. And well, I want to worry about a specific statistic on them that I'm sure maybe all of you have heard, that's the descents. So the descents are the positions in the permutation where the value drops. So for example, here, in this example of canon permutation, I have 5 in position 3 followed by a smaller entry 2. So that means I have a descent there. And another descent in position 4 because 2 is followed by a smaller number 1. And another descent here and another descent in position 8. And that's 4 descents in total. So for every canon permutation, I want to count how many descents there are. And that's what I'm going to denote by little des of the canon permutation, or for short of the dict path and the permutation pi that I started with. So I want to study descents on canon permutations. And that's not something we came up with in the first place. That was based on a paper of Sergi Elizalde, who studied descent polynomials, so descent generating polynomials for canon permutations. So when I fix a certain length and then I range over all dict paths and all possible permutations that can label them, and I get out the set of canon permutations. So he studied these descent polynomials, and one of the motivations was that essentially they're the permutations of the multiset with 2 copies of everything that avoid the patterns 1, 2, 2, 1 and 2, 1, 1, 2. So if you're familiar with that, you will see that from the definition in terms of up steps and down steps of dict paths, I can never obtain these patterns. And so they're also called non-nesting permutations, for the record. And the first, so Elizalde studied their descent polynomials and noticed that they have very nice structure. They're palindromic, they're real rooted, and they factor into nice palindromic polynomials, the Euler and Narayana polynomials. And then with Matthias Beck, we used this framework of PW partitions of Stanley to understand a little bit better these polynomials and establish more results about their distributional properties. But now for this talk, so that's the setup. And for this talk, we're not going to think about all possible dig paths and all possible permutations, labeling them at the same time. So what Elizalde did was to fix, well, one of his results, first of all, it was to notice that if we fix a permutation, for example, fix always the identity permutation to label the dig path steps, and then you range over all possible dig paths of this length and take the descent generating polynomial, you will always end up with an Arajana polynomial, which is a famous polynomial that enumerates peaks on dig paths. Or if you fix a different permutation than the identity, you will get, again, the Narayana polynomial shifted by a power of t. So in other words, that's just to convince you that the structure is nice. So what we wanted to study is the opposite. Instead of fixing p permutation and varying the dig path, we wanted to fix the dig path and vary the permutation. So again, that was just the motivation. For here, what I want to do is I want to fix a dig path d, and I want to consider the descent polynomial when I range over all permutations that can label its steps. So this is going to be CDT. And even if the examples should be pretty clear of what I'm talking about so far. So here is an example of a dig path of semi-length 3. What do? I write down all permutations with 3 elements. Then I take each one of them. I label the up and down steps, so I get out the corresponding canon permutation. And I am interested in its number of descents. So for the identity permutation 1, 2, 3, I get this word 1, 2, 1, 3, 2, 3. And that has 2 descents, in particular, this one here in the first peak and one more in the second peak. I do this for, I can keep doing this for 3, 1, 2. It's going to give me 3 descents and so on. And I summarize the information into a polynomial. So here CD is 3t squared plus 3t to the third, meaning that 3 of the canon permutations have 2 descents, same as the exponent, and 3 of them have 3 descents. So that's the kind of polynomials we were interested in looking at. And well, by looking at this simple example, you can already suspect some nice structure, right? And for example, this is too small, but you can already see some palindromicity maybe going on. So if I read the coefficients from left to right, it's the same as reading the coefficients from right to left. So the first question was to look into that. Are these polynomials also always palindromic, like the Narayana polynomials and so on? And the answer was yes. So to give you an idea of this, of why this is, it's very easy to see this proof. So for those that know, a plateau is 2 terms of when 2 terms of the permutation, 2 consecutive terms are the same. So adjacent terms are equal, but that happens in our canon permutations exactly when we have low peaks in the dig paths. Exactly then it happens that we have 2 adjacent terms equal. So essentially, the number of plateaus is determined by the dig path. So if I fix a given dig path, which is what we wanted to do, there is a certain number of plateaus that we denote LPK, the number of low peaks of my dig path. And with that into account, we can see that the descent polynomial will be palindromic. It's just that the center of symmetry will depend on the number of plateaus. So if I do this standard trick where I send I map permutations to themselves, where the smallest element is mapped to the largest, and so on. So 1 goes to 7, and so on. And apply this in canon permutations. So here in the canon permutation, 4 will be mapped to 3, 7 will be mapped to 1. So I had a descent that is going to turn into an ascent. So, and plateaus are going to remain plateaus. So you can very easily see that this trick works, and it allows me to show the palindromicity result with the center of symmetry depending on the number of plateaus of the low peaks. Okay, so they are palindromic. All these polynomials are palindromic, but still, we don't know what the degrees would be. It could be that, and it is that for this dig path, the first one on the top, we have degree 5, and the one on the bottom, we have degree 4. So why is that? That was our second question. And for this, we had actually to work a bit harder. It turned out the answer depended on the so-called bounce path of a dig path. So let me tell you what that is. I start with a dig path. Then I follow the same as Krishna's strategy for go-karting. So I start in the beginning, and then I go all the way straight, not turning until I bump into something. And then I turn around, and I go all the way straight again until I bumped into a wall. And I keep doing that, and that gives me a dig path, a bounce path, that is always under the dig path I started with in the dig lattice, and it's going to be the corresponding bounce path. So for any dig path, I can take out a bounce path in this way, in this process. So that's going to be bounce D. And it turns out, that's what we observed by running experiments on Feinstat, that the degree exactly is determined by the bounce path, and in particular by the number of peaks. PK is the number of peaks of the bounce path. So the explanation to the example from before, why these two degrees differ, is because the two bounce paths corresponding to these dig paths differ in terms of the number of peaks. So one has 2 peaks and one has 3 peaks, and that explains why the degrees are different. But of course, then you can wonder other things. For example, why are the leading terms different, and how can we determine the leading terms, especially and that means determining also the smallest term by palindromicity. For example, the constant term or the smallest non-zero term. How can we understand when they're equal to 1 or when they're not, or what are they? So that's to give you a taste of that's another direction we looked at. The leading coefficient now, after finding the degree and observing the palindromicity. Right, so for this, we came across an idea similar to bounce paths. It's a class of paths that are almost bounce path under my dig path that I start with. So here in blue is this dig path I start with. And then I want all paths under it that have the same number of peaks as its corresponding bounce path. And they are under it in a reasonable way. And its valley of them is either on the floor, it's at height 0, or it's exactly on the level of the dig path. It doesn't leave the dig path. So one of the two. And this family seems to have, this family of paths under my dig path seems to have a good behavior, and it gives us a lower bound for the leading term of these polynomials. So for a polynomial, for a dig path D, I take the corresponding descent polynomial of its canon permutations for this D, and the leading term is bounded below by the number of paths that are almost bounce paths. And then, yeah, of course, some constructions were involved that I cannot get into the detail here. But essentially, we got a bijection between the descent sets of the maximizers of those polynomials. So meaning, I want to understand the leading terms of this polynomial CD. So I want to understand what are the canon permutations, set MD here, contributing to the leading coefficient. And these canon permutations contributing to the leading coefficient, these maximizers of descents, they have descent sets that are in bijection with peak sets for these almost bounce paths. Okay, and yeah, maybe that picks give you an idea. I have remarked here not the descents but the non-descents positions with a dot, and then I can always construct sort of this red buff under that realizes the non-descents as its peaks, and it lies in this set PD that we talked about. So it's at least a bound, it's a start, and in fact we were able to characterize exactly the leading coefficient. I'm not going to get into the details here, but the idea is that for each of these paths that we saw, they're almost bounce paths. Here before we had 3 examples. There is a corresponding poset that you can build, and then by looking at the linear extensions of this poset, you can write down all the maximizers coming from each of the paths under it. And if you take the collection of maximizers altogether, that gives you the total number of maximizers, and that lets you count what exactly is the leading coefficient of your polynomials. So we have this method. Of course, there is room for more efficient methods and more explanations and lots of questions. I just want to say that one other natural question would be to ask if these polynomials are palindromic, real rooted or similar. But as we already saw, they don't have this property. Unfortunately, they're not always palindromic. So what we were able, the furthest we could push it in that direction is that we could show that there are no internal zero coefficients. So that means I cannot have a zero coefficient surrounded by two non-zero coefficients. And that was also a fun proof because it involved finding an induction to do preserve with the suitable number of descents and so on. Yeah, but that's more or less what I wanted to talk about. And there's many open questions that we highlight on the paper. For example, the other coefficients, we need techniques for the other coefficients of these polynomials. We need higher dimensions means higher dimensional dig paths, which boils down to linear extensions of posets. We don't have any progress there. And there's also several connections to other sequences in the OEIS or or Catalan numbers that we could understand better. So that's all. Thanks for your attention.